can hear me. Yeah. Okay. Yeah. Thanks. And it's really nice to see so many familiar faces here after so many years. Yeah, really appreciate your coming. So I'm going to talk about a short overview of the project. Typical modern technology.
Yeah. It has to go somewhere, unfortunately. But
yeah, that's fine. That's fine. That's fine. That's fine here. And but I can't move the screen. It's not going down. Why? Can't get this done. This. Oh, here I got it. Okay. So I'm going to talk about a few parts here. First, give background information. Then I'm going to talk about satellite number one, satellite number two. Then what's important about the sciences in connection with satellites. Then finally, give a summary. Okay. I think in the geomagnetic field is most important geophysical quantity or parameters which you can use to understand the phenomena of the whole Earth system. And this is because the satellites measure magnetic field is from various different parts of the Earth, from Earth's core geodynamo, from mantle-induced magnetic field, from ocean current-induced magnetic field, from crust magnetic field, from ionosphere and magnetosphere. So this magnetic field you observed actually contains all the important information which you can use to understand a system. We have done a lot of software and hardware in the core for number one satellites. So this picture just shows we have satellite station which automatically track the satellites number one and receive magnetic measurement from number one. And also we have this data center. We have like 3,500 CPUs there to process the data we received from satellites. So we have this fantastic hardware and software in the core, which has been built over the past few years. Okay, first, I would like to say a few words about the number one satellites. So number one satellites is lower latitude satellites. The angle is about 41 degrees and nearly circular orbits around 455 or 50 kilometers. Okay, it have scientific instrument of scalar magnetometer, vector magnetometer, and other important instrument for the ionosphere and for plasma measurement there. It was launched on the 21st of May of this year. And second satellite in the number one, because number one twin satellites, the 1B, we call the satellite 1B, contains more instrument about measurement of the space weather, space physics, like X-ray detectors and charged particle detectors. So the idea is how number one, number two working together. The number 1A focus on the geomagnetic field, the number two or number 1B focus on the space weather physical parameters there. And if you look at the picture, which is real satellites before launch in DFH, it's huge. It's huge, really. The 8.5 meters long is really huge satellites. And this is, hopefully I can, I was there. I was there. I was there for the launch. Oh, sorry. I was there for the launch, which sits there about 100 meters, a few hundred meters away. The noise is enormous. The noise is really enormous. Very, very excited. So how about the number two? Number two would be quite different from number one satellites. So number two, we have twin satellites as well, two satellites. 2A, 2B are almost identical, but they are in different orbits. So instead of circular orbits, there'll be elliptic orbits with perigee about 190 to 200, around 200 kilometers. The idea is to use these satellites to collect information in a three-dimensional way. And that 2B should be, my idea is say, if I have 2A, if 2A is in the North Pole region, the 2B should be in the South Pole region. So there should be collect information simultaneously, but in different hemisphere, which provide information about Northern Hemisphere and Southern Hemisphere. So that's an idea. I think an important characteristic about the number two is it's close Earth perigee around 200 kilometers and would be able to cover the whole Earth from Northern Pole to Southern Pole about 2 to 3 months because the perigee drift. The period drift from North Pole to South Pole is about 2 and 3 months. You should be able to provide three-dimensional measurements instead of the two-dimensional. For example, MSS1 provides two-dimensional measurement on the surface about 450 kilometers. But this one will be from three-dimensional, collect our information from 200 kilometers to a few thousand kilometers. So provide three-dimensional measurement of the magnetic field and the space parameters there, okay? And another important scientific issue which are concerned is the coupling zone between ionosphere and magnetosphere, which are around 200 kilometers. So if we can have the satellites which measure from 200 kilometers to a few thousand kilometers every day, that would be able to provide the important unknown information about the coupling zone between ionosphere and the magnetosphere. That's another important scientific objective here. So scientifically speaking, we want to have this perigee as close to Earth as possible, even less 200 kilometers, and this apogee as far as possible. But the engineer tell me, no, say you can't do that. And because if you want too close, they have too much fuel. If you're too far away, they have too much radiation. So we have to compromise. I think we're still in the process doing calculation. I think its perigee is about 200 kilometers. The apogee is about 2,000 kilometers. So that's sort of idea acceptable by engineer limits. That's what we try to do here. So the scientific research in connection with this constellation is really trying to understand from Earth's core to the magnetosphere, because we would be able to measure all these different sources of magnetic field from Earth. Okay. So it's first we try to understand dynamo generated magnetic field. As everybody knows, in order to simulate Earth's dynamo realistically is almost impossible because its Eckman number too small and all the parameters too extreme. So, but if we have continuous accurate measurement, and that would be helpful for us to forecast magnetic field with the modern technique of the simulation here. Okay. That's the first objective. And the second objective of this constellation is try to understand the flow structures in Earth's interior from these accurate measurements. Instead of deal with fully dynamic problem, we can neglect the Lorentz force on the flow, and then we can do some simple semi-kinematic problem, such that we would be able to understand the core flow like Chris Finlay, they did several times ago, if we combine the observation, circular variation together with the observation with this structure of the inertial modes problem, then we would be able to provide some kind of three-dimensional structural flow in Earth's interior. And another object, we try to understand the mantle conductivities. We have done quite a bit of research over the past few years, and because mantle is conductive, so therefore, if you form the mathematical problem in a very nice way, you should be able to inverse the magnetic conductivities of the mantle by solving these simple equations, vector equations, okay? So that's what we try to do as well. And third is we try to understand the cluster magnetic field. And we try to, if we have a good observation, accurate measurement, particularly for perigee is around 200 kilometers, we perhaps would be able to increase the accuracy by order of magnitude from this measurement of the constellation. So that's what we try to do. And we perhaps try to use a different method. Instead of using, we use the method which proposed by Dave Gubbins several years ago, which I find is really mathematically elegant approach to this kind of problem. So we also try to work on the cluster magnetic field based on the constellation. Another important issue is ocean-induced flow. When you look at the ocean-induced magnetic field, which is about 20 or 30 NT, the problem actually is mathematically straightforward, because what you have to do is to solve this vector Helmholtz equation. But the boundary condition, the geometry is terrible. And if you want to solve that problem, then you have to you can't use the spectral method. You have to use like a finite element method or local method, such that you can solve this vector Helmholtz equation in a very important, very complicated structure of the geometry to get your results. But that's important. And also important is you have two parts of the circulation. One part is almost stationary, another part is tidal, which is time dependent. How to separate them is also mathematically, physically challenged problem here. And again, it's in the space, ionosphere, magnetosphere, we try to understand what's going on there. In particular, I think we try to understand the coupling regions between magnetosphere and ionosphere, which is around 200 kilometers. This region we know very little about. I think what I understand is why is we know very little is because for balloon is too high, for the satellites too low. So this region around 200 kilometers have very, very little data. So if we have this number 2 satellites, then we would be able to map the three-dimensional way in this coupling regions there. So I think that'd be extremely helpful for scientists to understand magnetosphere and ionosphere and this coupling mechanism there. And as a summary, I would like to say is we are working real hard to try to get this constellation as early as possible. The first satellites have been launched. The calibration process going smoothly. Thanks so much for DTU's help and for Austria's help. And I think MS1 is really close to its end of calibration now. So my idea is try to push forward the second satellites to be launched as early as possible, such that number 1 and number 2 can form constellation. It will be really nice idea if we can launch the number 2 twin satellites in 2025, that's a year and a half from today, then this number one and number two can come together, working together for another 5 years, provide the important and useful data for scientific community over the next 5 years. I hope we can achieve that objective, and thanks so much for your attention. Thank you.